Hello everyone. So this is the second video lecture on the ring theory. So let us recollect some facts that what we studied in the last class, and we move further in studying the properties of integral domain and the field. First of all, let me recall the first definition is what's a ring. As we studied earlier, there are two operations equipped with a non-empty set R. It is said to be a ring. With respect to addition, it needs to satisfy few properties. That is, with respect to addition, this should be an abelian group. Second is, with respect to multiplication, it should be a semi-group. In the sense, it needs to satisfy closure law and associative law. After this, with respect to both addition and multiplication, it needs to satisfy distributive law. That is, A into B plus C, it is AB plus AC. A plus B into C, it is AC plus BC. So this is the distributive law. If it satisfies these properties, we say that it's a ring. Second definition that we want to study is what is an integral domain. Already we know what is a zero divisor, so we are just moving on to integral domain. It's an commutative ring. A commutative ring with unity which does not have zero divisors. This is said to be an integral domain. Z is an integral domain, and in fact Q is also an integral domain, R is an integral domain, C is an integral domain. We will come back to this a bit later stage. First let me know the definition. Then we studied what's a field. Field is a commutative ring with unity in which every non-zero element of, let me say, a commutative ring R, every non-zero element of R as it's invertible with respect to multiplication, as a multiplicative inverse. That is, we say that for the inverse, if it is invertible, we use the name called unit. That's the difference. There is a difference between unit and unity. That's what we observed in the last class. Again, we just think about these two cases. So what's an integral domain and what's a field? So our study, today's study is only about these two facts. Is it clear? For this, we move on to some standard results. First result is, in an integral domain, cancellation law holds. So it's a proposition. Cancellation law holds in an integral domain. As I already mentioned, we think about the cancellation law with respect to multiplication. With respect to addition, cancellation law will always hold because it's a group. Is it clear? So that is what I meant was, if R is an integral domain, let R be an integral domain. I just write it as ID, which is an integral domain. If A and B and C are in that ring R, or else an integral domain R, provided A is non-zero, if given AB is nothing but AC, then that should imply me B equals to C. So this is the cancellation law. So proof is simple. See, AB equals to AC, both have same quantity. This will imply me AB minus AC is 0. This will imply me A times B minus C equals to 0 by the distributive law. Since A is given non-zero, so this is 0. But how to say B minus C is 0? Let me assume, sir, if B minus C is non-zero, then what is the case? If B minus C is non-zero, A is also non-zero, B minus C is also non-zero. That will conclude as what? That will conclude as, if B minus C is non-zero and A is also non-zero, product of two non-zero is 0. That means it has 0 divisors. If this happens, R as, that will imply me R as 0 divisors. That means R cannot be an integral domain. But we have R is an, we are in the integral domain. So this cannot happen, it's a contradiction. So that contradiction will force us to conclude B minus C must be 0. If B minus C is 0, B is nothing but same as C. That is the cancellation law. So cancellation law holds good in an integral domain. Is it clear? Again, second fact that we study is, this is interesting. What is the relation between field and the integral domain? What is the relation between field and integral domain? Is there any relation between these two? How they are related? So that I will give to I will try to give you the conclusion by the end of this class, how to think about these two. However, the first theorem I am going to prove here is, I don't know to deal with the infinite integral domain, but I will consider a finite integral domain in my hand. If I have a finite integral domain, it's a field. That will imply me it's always a field. That is, the theorem is, every finite integral domain is a field. But how to prove this? Proof is simple. I already have an integral domain and it's finite. I need to show it's a field. So first of all, let me try to understand what is an integral domain. That's the need of recollecting those facts in the beginning. Field is a commutative ring with unity. Integral domain is also a commutative ring with unity. So these things are common. Am I right? But what's special in the field? I need to show every non-zero element is invertible. Every non-zero element is invertible. Is it clear? So if I choose, I start with this, R be an finite integral domain. If it's an integral domain, I can claim it's a commutative ring with identity without zero divisors. So these properties are there for this. Okay. Now, in order to show R is a field, it's enough if we show every non-zero element is invertible. Why? Because It's already a commutative ring with unity or else identity. If every non-zero element is invertible, then it's a field. Is it clear? So I have an finite integral domain. Now I need to show it's a field. That's all. But in order to show it's a field, commutative ring with identity is needed. That's over. Just I need to say every non-zero element is a unit, or else it's multiplicatively invertible. Every non-zero element is multiplicatively invertible. So invertible, we use one more name for this. It's called a unit. But how to show this? Okay, so very easy. Try to understand this. So since my business is only with non-zero element, I consider let A be a non-zero element of the ring R, or else an integral domain R. Now I define a map F from R to R to be, if X is there, let it map to AX for all X in R. That is, F of X is AX. That is the rule I define. Now what I will show is this map F is 1 1. What is the need of showing this F is 1 1? We'll come to it. So let me show it's 1 1. Let me assume F of X is equals to F of Y. That will imply me AX is AY. Since A is non-zero, I can cancel this, because in an integral domain cancellation law holds. Don't cancel it likewise. Just write AX equals to AY. It will imply me A into X minus Y is 0. Since A is non-zero, I can claim X minus Y is 0. That will imply me X is Y. So if F of X equals to F of Y, I got X equals to Y. That is F is 1 1. See, the virtue of this function is, once you have finite set, let me say set is same. Here also R, here also R. So it has 1, 2, 3, 4 elements. Here it has 1, 2, 3, 4 elements. Let me say, if it is 1 1, that means one fellow will meet only 1. Then exactly it is onto. You can just check, since it's with the same set. So it will be onto. So since F is 1 1 with itself, that is the sets are same. That's what I said. F is 1 1 with both domain and codomain are same. Then I can say F is onto. So this property is needed. Is it clear? Once I have F is onto, what can I do with this? See, whether 1 is here, whether 1 belongs to this. Exactly, because it's an integral domain, so it's an commutative ring with identity. 1 exactly here, it is there, identity is here. So 1 is somewhere here. If 1 is here, it's onto means I can find the pre-image. Is it clear? If this is the image, I can find a friend who made him to come here. So I can find a friend here. Who is that fellow I need to find? So since F is onto, 1 belongs to R. Clearly, 1 is in R. If 1 is in R, since it is onto, I can find a member here. Let me say B is here. So since F is onto, there exists B belongs to R, such that B is the fellow who made him to come to 1. That is, F of B is 1. Once I throw that member B with a rule, he will just fall into the place 1. Now, what is F of B by our map? So, F of X is AX. F of B is some AB. Is it clear? That means I took A to be non-zero. I took A to be non-zero and I can find the inverse. B is there such that A into B is 1. That means B is the inverse for A. Is it clear? If you define f of x equals to x into A, you will get BA. That's all. So this will imply me A into B equals to 1, which is equals to BA. That means any non-zero element, I took one element, it's arbitrary, B arbitrary. So for an arbitrary element I can find an inverse. That means you choose any element. I chosen this, I choose an A somewhere here, you choose some B here or else some C. You will get the inverse for that also. Arbitrary means that you can, it's left to your choice. So A into B is 1, which is nothing but B times A. That means every non-zero element is a unit. It's invertible with respect to multiplication. If every non-zero element, that's what I needed to show. If R is a field, I need to show every non-zero element is invertible. I shown here, every non-zero element is invertible. So that will imply me finite integral domain is a field. Is it clear? Now you can ask me one question. Can an integral domain, can it be a field? Need not be. Why? The example is, let me say Z. Z is an integral domain, but it's not a field because 2 is in Z. I cannot find the multiplicative inverse. 1 by 2 is there, it will give me 1, but 1 by 2 doesn't belongs to Z. An integral domain need not be field. But finite integral domain, it's always a field. Is it clear? So this is the one theorem. Then I can say next corollary to this is, for any prime P, ZP is always a field. Why? Because proof is easy. ZP is an integral domain. Let me show ZP is an Let me show this. ZP is an integral domain. How to show this ZP is an integral domain? Of course, it's an commutative ring with identity. Just you need to show it doesn't have any zero divisors. That is, let A bar B bar be equals to 0. Let A bar B bar be 0. So if it is 0 means it's a multiple of P. Am I right? For example, Z5 is there. 0 bar, 1 bar, 2 bar, 3 bar, 4 bar. What is 5 bar? 5 bar is 0 bar. This is 5 bar. What is 6 bar? This 7 bar, 8 bar, 9 bar. What is 10 bar? 0. What is 11 bar? That is 0. So this is a residue. That's why it resides many elements. That's why it's called residue. 0 bar, 5 bar, 10 bar, 15 bars. Likewise. So however it is, 5 will divide this, 5 will divide this, 5 will divide this, 5 will divide this, 5 will divide this. Is it clear? So it's a multiple of 5, that's all. So that means here also P will divide this. If it is 0 means it's nothing but it looks like some multiple of P. It's a multiple of 5, it's a multiple of 5. 15 is a multiple of 5. Similarly, A bar into B bar is a multiple of P. Is it clear? So P divides AB. Property of prime. If P divides AB, that will imply me P divides A or P divides B. That is, A is a multiple of P or B is a multiple of, that is, A is a multiple of some P. I written it as P times K1. B is a multiple of P again, where K1 and K2 are any integers. Now what is A bar? R is there. What is A bar? Apply that congruent modulo with respect to P. Since P is there, it is 0. R What is B bar? Since P is there, it is 0. I took product of two elements, A bar into B bar is 0, and I'm getting either this is 0 or both cannot be non-zero. That's what it says. That means it doesn't have 0 divisors. So ZP has no 0 divisors. Since ZP is a commutative ring, with unity or else identity, I can say ZP is an integral domain. Is it clear? But how to claim it's a field? How many elements are there in ZP? How many elements are there in Z5? 0 bar, 1 bar, 2 bar, 3 bar, 4 bar. So 1, 2, 3, 4, 5 elements are there. Similarly in ZP, P elements are there. That means finite. So ZP is an integral domain as well as it's an finite set. So it's an finite integral domain. So by last theorem what we studied, finite integral domain will be always a field. So ZP is an integral domain as well as it is finite. So it's an finite integral domain that will claim, that will serve the purpose. ZP is an field. Is it clear? But that is not the case with respect if you take some Z6. Sir, what is the case with Z6? Whether it will be a field? Need not be. 4 bar, 5 bar and 6 bar. 6 bar is 0, 5 bar up to 5 bar. Now, 2 into 3 is there. It's 6, which is nothing but 0. So, here Z6 is not an integral domain. It's not an integral domain itself. How to say it will be a field? Because finite integral domain will be a field. It's finite, but it is not an integral domain. Is it clear? Now the question is, one more question will strike our mind. See, we studied what? Finite integral domain is a field. Finite integral domain is a field. Whereas, what can you say about infinite integral domain? Whether it will be a field? Question mark. But this need not be. Example we give is Z. It is not a field. Next question is, what can you say about field and integral domain? Coming this way is okay. What can you say about this? Whether every field is an integral domain? Whether every field is an integral domain. This is interesting. Answer is yes, every field is an integral domain. That's what I mentioned in the beginning while taking the examples for integral domain. I took Q and R and C. These are fields. Every field is an integral domain, undoubtedly. But how to show this? Every field so first of all, what we want to show that it's an integral domain, it should be a commutative ring with unity, or else we can use, some author will use it as identity. So first thing is this, then it should have no 0 divisors. If I want to have an integral domain, these two are the demands. But what is a field? Field is already a commutative ring with unity. That means first demand is already proved. It's a commutative ring with identity. What is the second claim? I should show that it has no 0 divisors. That is the fact that we want to concentrate. That is, it's sufficient if we prove field has no zero divisors. But how to show that it doesn't have any zero divisors? So for that, I try to prove this result. Theorem. Any field R is an integral domain. As I said, it's sufficient if we prove R has no zero divisors. So that is, we assume let R be a field. Okay. Then all these conditions will fall. It is sufficient if we prove that R has no zero divisors. But how to show it doesn't have any zero divisors? So let x into y be 0, where x is non-zero and y is non-zero, belongs to R. It is, I took two non-zero elements. On contrary, I am assuming x is non-zero as well as y is non-zero, such that their product is 0. What else I am assuming? On contrary, it's a contradiction. Getting my point? Because I need to show it doesn't have any zero divisors. But I am assuming it has zero divisors. Product of two non-zero element is 0. X is non-zero, y is non-zero, but their product is 0. So on contrary, let us assume the product of two non-zero element is 0. But since x is non-zero and it's in R, what is the properties of R? R is a field. It's a field. If R is a field, every non-zero element is invertible. That is, x inverse exists. So multiply by x inverse here. X inverse x, y, it is x inverse times 0. But x inverse into x is 1. 1 into y is y. Here x inverse into 0 is 0. That will give me y is 0. But I assumed y is non-zero. But I am getting y is 0. A contradiction. Why this contradiction? Because I assume the false thing that it has zero divisors. So it does not have zero divisors. That is, R has no zero divisors. So being a field, R is already a commutative ring with unity which doesn't have zero divisors. That will conclude as any field is an integral domain. Is it clear? So probably we had answered what is the case for finite integral domain and what is the case for infinite integral domain, and what else can you think about? If it is a field, can I think about it's an integral domain? Yes, that also we can show. So in the next class we will describe few problems. I will try to just I want you to try those things. Kindly try this. Every non-zero element of Zn is either a unit or a zero divisor. So kindly try this. And second question is, give an example of skew field. Okay, already we studied what is a skew field. Is it clear? Or else division ring. Try to give the example for this. With this we conclude the class and we try to prove this particular problem in the next class and try to give an example of a skew field, and we solve some of the problems, and we will try to think about what are subrings and how to think about the subgroups, as well as what are the operations that we can think about subgroups. For example, if I have a subring, a collection of subgroups, what about their intersection, what about their union? This and all will strike our mind. So similar to what we studied in group theory, if I have a collection of groups, intersection of two subgroups is a subgroup and union need not be. Here also we can work on the parallel way, and we will come to some conclusions once we discuss those things. But however, you can just look into these things, and you can refer Dumit and Foote for this. You will get the answer. Okay. Thank you so much.